and this is more of a non-technical guide for business dummies. Um, since we have not gone through an econometric course, this is going to be like a brief overview of how to and what the science behind regression analysis really is about. So, why are we even here? Business graduates, business students, why do we really even care about regression analysis? Well, because maybe we think we're researchers and we're taking courses like research methodology and methods in business research, and maybe even think that we are scientists. Maybe we're interested in this particular lecture because we have understood that the world these days is based or driven by data, and data basically helps us make better decisions, and regression analysis is one way to actually analyze data. So what we're trying to basically do is we're trying to explain how the world works, and what you see over here is an example of a scientist trying to explain how the world works. Here's another example of a scientist explaining how the world works. So these are examples of people trying to explain based on their ability how the world works. But this was all on a lighter note. We understand that these guys are not very scientific when they are approaching or trying to explain these ideas, and maybe not even serious about them. But as people who are trying to be researchers or have a course on research which requires them to do some kind of explaining of how things happen in the world. In this class today, we are going to be discussing how the world works. So we are going to be explaining a phenomena in the world and how it works. And for today's session, we'll talk about how or what explains people's wages. So we all know that wages vary across people. So my wage might be different from yours, and there must be some factor that kind of differentiates or is the reason why my wage is different from yours. So we want to explain the variation in the wages of people, and this is where we are trying to explain how the world really works. And for today, our research question basically is going to focus on whether education affects people's wages. So, once again, the focus is whether education impacts wages. So, we know wages vary, but does education explain the variation of wages among people? Now, in order to answer this particular question, um, and remember that we are trying to be scientific about it, we are trying to be rational about it, we want to be data driven when it comes to making conclusions. How do we go about testing this? So, what we can actually do is, in order to see if higher education leads to higher wages, we can carry out a survey. We can ask people their wages and education. Once we have this data, we can actually plot them, plot this information on a graph where we can have education on the x-axis and wages on the y-axis. And by looking at the data, we can actually try to see what the data tells us about the relationship between wages and education. Um, So by looking at this graph, by the way, is called a scatter plot. Each point over here represents a particular person who was surveyed, and he gave some information about his level of education and his wage. So by looking at this plot, I wonder what you see over here. So when I see this plot, I feel as if people who have low education have lower wages, and as their education goes up, we see people with their wages going up. And the best way to actually look at this is to draw a line, or a best fit line, that cuts the data into uh, equal halves. And a positively sloped best fit lines maybe suggest that wages and education are positively correlated. Higher education would lead to higher wages, and that kind of makes sense as well when you think about it. Um, um, when you look at this best fit line, I'm sure most people would be thinking in terms of this being a straight line, and this being a straight line therefore implies that this would have an equation where wages would be y, and then you'd have an mx plus c sort of equation for the straight line. And based on this red line that I've made, the m would be a positive number, and whatever the value of m is basically implies that as education increases by 1 year, wages would go up by the value of m, which is the slope over here. So this is basically a straight line. This is what we've talked about. I'm sure you know about how the gradient basically tells you run over. It tells you how y changes when x changes by a unit. And for example, if you had an equation that looked like y is equal to 2x plus 10, the 2 over here is the gradient, and it's telling you that as when x changes by a unit, y would increase by 2. And the same actually follows for the regression sort of thing that we're going to be seeing in today's session. The beta ones, and the beta 1 in this case is basically sort of like the gradient, and it tells you that when education changes by 1 unit, how does wage change. So the interpretation is similar. Based on what we've seen so far, it seems as if our job is done, and we've just proven and explained how the world works, and explained how wages and education are related. And just by looking at the scatter plot and the best fit line, we can conclude that there is a positive correlation between wages and education. Higher education will lead to higher wages. Problem solved. There you have it. But unfortunately, that is not all, because all we've proven so far is that when education goes up, wages also go up. We've shown a correlation between education and wages, but the problem is that correlation, does not imply causation, and let's just see a couple of examples over here that prove the same. So the graph that you see over here shows us people's consumption of margarine, and how it's strongly correlated with divorce rates in this particular place. Uh, so the more margarine you eat, the the higher the divorce rate. Uh, these are highly correlated, but is one causing the other or not? Probably not. Um, how about this? Um, when Margaret Robbie appears in movies, as the number of movies she's appearing in goes up, wind production generated in this particular island goes up as well. So obviously, what we can see over here is that although these two things are correlated, they're moving together. One is not causing the other, and since it's not causing the other, we're not able to say that one results in the other. It's just two things moving together. And as of what we were discussing till this point, all we've said so far by establishing correlation is that wages and education move together, but there is a probability that maybe education is not the reason that causes higher wages. Maybe it's just a coincidence. Maybe it's just spurious results. By chance, these two things are moving together. And that's the problem that we're facing over here. And I'm sure there must be many other factors that affect people's wages, right? And for this session, maybe experience would impact wages. People's time spent with an organization, which is tenure, might impact wages. Higher tenures might lead to higher wages. Gender might be a factor that impacts wages. Mostly men get paid higher wages compared to females. So maybe that's one factor that might explain how or why wages vary amongst people. So there can be many factors that can impact wages. And just to reiterate, we're trying to figure out what causes variations in wages. That's the real world phenomena we're trying to figure out. We want to explain this. Um, so, education is what we want to really look into. We think education might be impacting wages, but then we've just identified three other things that might be factors that might be affecting wages as well. So, how do we kind of um, establish causation? In order to establish causation, which is basically saying that education increases in education causes the wages to go up, we need to kind of hold tenure, experience, gender constant, and then maybe if we can increase education and wages go up, we can actually say that since tenure, experience, gender was not changing, changing education resulted in wages changing. Therefore, we can now, with surety, say that education actually impacts wages. But do we do that? This is not one of those cases from primary school where we were growing red lentils, or were doing experimentations on photosynthesis where we'd be growing plants, and as an experiment where the plant needs sunlight and carbon dioxide and water and minerals to grow, you could always put the plant in a shade and maybe not give it water or fertilizer, and control for those factors to actually see if one of the other factors uh, had an impact on um, the plant actually growing or not. So, in the case of a natural experiment, we can control such factors as like sunlight, water, or fertilizer. But in our case, since we are social science, we're working with human beings, controlling people's experience or gender or education is difficult to do. How do we really go about doing that? And this is where the regression analysis comes into uh, the picture, and it kind of helps us mimic a natural experiment. So with regression analysis, what happens is through some fancy statistics and maths, the value of this beta over here tells you the impact of a change in education of one unit on wages, assuming education, tenure, and gender does not change. Similarly, beta 2 tells you how wages change when experience increases by unit, holding all the other three factors constant. So, what's happening over here is that these betas take out the effect of the other betas and only tell you the effect of a change in their parameter, assuming the other parameters are held constant on wages. So beta 3 over here, beta 3 over here, this is a type over here, tells us how wages, the dependent variable, changes when tenure increases by 1 year, and this value is equal to the value of beta 3. Gender 4, beta 4 over here is tricky because gender is either a male or a female, and so when you switch from male to female, the value of beta 4 tells you how the wages change across different genders. And finally, the last thing over here is this mu you see in the equation, which is the error term. Notice that experience, tenure, and gender are not the only factors that impact wages. There might be multiple factors that we've missed out. And with this error term, the error term signifies all those other. It's basically um, includes all the other factors that impact wages that were not included in the model. This way, we are actually able to show that all factors that impact wages are included in our modeling. So once again, factors that we did not include in our model automatically enter into the equation through this error term. So now let's talk about how we go about things. So you go about carrying out a survey in which you ask people their education, experience, tenure, gender, and wage. And through the survey, you now have a lot of data with you. Um, I'm sure we have a little bit of understanding on different types of data. This analysis that we're currently going to be looking into is a cross-sectional analysis, considering that it's a one-time survey data collection activity that we did, and it's not over longitudinal in terms of time. Um, we can then enter all the data that we collected into Excel or eViews or Stata or SPSS. There's some softwares that can be used to run a regression. And this output you see over here is an output from Stata, and with our MBA class we have actually before the mids talked about how to run a regression that looks something like this. um, so the output, let's just talk about the output. The output will have an ANOVA table, which will and then you have a dependent variable, which means we are trying to explain wages. And what are the factors that are being used to explain wages? These are the independent variables, so education level, experience, tenure, and whether you're a male or a female. In this case, we're using female as the dummy variable over here to explain gender impact. And then on the right hand side you have another box. This box over here tells you whether your model is good or not. So at the moment our model is basically wages being explained by education, experience, tenure, and gender. So this box over here explains to us whether this model that we've chosen to kind of explain the variation in wages, is it good or not. So The coefficient over here are all the beta values that are associated with the parameters. So the beta value for education is next to it. Then you have the beta value for experience, tenure, and then gender. It is important that when you're looking at these coefficients, you look at the size of the coefficient as well as which is the magnitude, as well as the sign as well. So positive signs basically say that when education increases by 1 unit, wage, since it's a positive sign, increases by this amount. When experience increases by a unit, wage increases. But in this case, with gender, if you are a female, since this is a negative value, wages decrease by this much. um, the table also talks about how much data was collected. So when this data was being collected, 526 people actually gave information on their wages, education, experience, tenure, and their gender. The R square. So you have an F statistic and an R square. An F statistic basically is used to actually tell whether your model is actually a good model or not. And the way it's done is that this F statistics basically says uh, that it basically compares a model the model that you have with a model that didn't have any of these IVs, and sees if including these independent variables has significant impact. Ideally, this number for the F value should be greater than 4, and the probability value should be less than 0.10. Then you have an adjusted R square. So you've got two kinds of R squares. One is the R square and the other one is an adjusted R square. So the R square basically explains. So you're trying to figure out or trying to explain the variation in wages. Wages vary across people, and you want to kind of explain wages or variation in wages through education, experience, tenure, and gender. And the R square tells you how much of the variation in wages is explained by your model. In this case, these four variables explain 36% of the variation in wages. And so recall, you want to explain how the world works. You want to explain how wages vary. And R square tells you how well you are explaining your dependent variable. So out of the total 100% variation in wages that's happening, our model explains 36% of the variation. There's another adjusted R square over here as well, and we'll discuss that in a minute. But what is important is that we look at the coefficients over here and notice that this minus 1.56 is the constant. This is beta naught. And then you have the coefficient of education is 0.57. I've added this over here, and then you have the coefficient of experience, which is 0.02. For tenure is this, and for gender it's negative 1.81. I wonder if you could interpret that. So remember, with the straight line equation, this is like the gradient, and it says if this changes by 1 unit, the dependent variable changes by this amount. And the great thing about regressions equations is that these effects are assumed to be held constant, which means that 0.57 is a partialed out impact of education on wages. It does not include tenure impacts of tenure, wages, and experience in it. So what we can say is a unit increase in education would result in wages increasing by 0.57 units. A unit increase in experience would result in wages increasing by 0.02. A unit increase in tenure will result in wages increasing by 0.14. If you are a female, wages would be lower by 1.81. But what's important to remember is that these betas that you're getting are impacted by how you enter your data into the software. So you can use wages in thousands or in lakhs. It will result in the value of the beta being different. You can use education. Education will probably be used as a year. Experience, on the other hand, could be months as well. So how you enter your data into the software will kind of impact the betas that you're getting. And another thing that's very important to remember is that normally data, when it's being entered into the software for running a regression, it is sometimes transformed. And when I say transformed, this equation over here can be transformed by taking not using wages but log of wages, not using education but log of education, not using experience but log of experience. Same for tenure. So you can have a linear equation in which wages does not have a log, education does not have log, experience does not. No variable has a log, either the dependent variable or the independent variables. Or you could take logs of the whole equation, where your dependent variable is in the log form, and so are your independent variables. Or you could be in a log linear format where your dependent variable has a log, but your independent variables do not have logs. When you do such kind of transformation with the data that you've collected, the interpretation or how you interpret the beta changes as well. So when you have a linear equation, a lin sort of regression model, uh, these coefficients are interpreted in terms of unit change, which means that education increasing by a unit will cause wages to go up by a unit, by this amount in terms of units, by this many units. Tenure going up by 1 unit, in this case 1 year, would result in wages going up by this amount of units. However, when you take logs, so if you had a log sort of, so if you had the second case, the beta would be interpreted in terms of percentages, which means that so for example, see if you see this slide over here, I've estimated the model as a linear model. Then I've estimated it as a log dependent variable, and the remaining are linear. So log lin model, and then I've estimated the log model as well. So notice that the coefficients are different in all three cases because you've transformed your data. And how you interpret the coefficients changes when your equation or the econometric equation is in whichever form it is. In the case of the log formula, for formulation of the equation, this beta 1 over here is interpreted as a percentage change. So you say, if so, for example, over here, if you talk about education, log education, the way you interpret this coefficient is you say that when education increases by 1%, wages increase by 1.01%. Whereas in the lin case, these were units. When education increased by a unit, wages increased by 0.57 units. And you can take a look at, pause the video over here and take a look at the lin log and the log linear uh, representations and see how the way you explain the beta changes in these three scenarios. So now that we've seen this, we can actually interpret what we found out. And what we're saying over here is that when education increases by 1 year or 1 unit, wages increase by 0.57 units, assuming gender, tenure, and experience remain the same. What we're saying is that when experience increases by 1 year, wages increase by 0.02 units. See how I'm using units because this is a lin or a linear uh, equation where the dependent variable is also linear and the independent variables are also in the linear form. If these were in the log form, then we'd be saying using percentages rather than units in our analysis. Similarly, when I'm kind of not very inclined to interpret gender over here because gender takes the value of 0 or 1, and in our estimation we're using 1 for a female and 0 for a male. So in the case of a female, the wages are less by 1.81 compared to the male. Now that you've actually seen this, we want to kind of think about whether what we've done, whatever we've estimated, was that a good model or not. But first, we want to kind of refocus on what we were trying to do. We were trying to explain how the world works, and our focus at the moment is on explaining how people's wages vary, and between people, uh, the wages we know vary, and wages in our case is the dependent variable because that's the one that we're trying to explain. And we've so far decided that education, experience, tenure, and gender are factors that explain how wages vary. In order to kind of see whether our model is a good model or not, we look at the R square, we look at the adjusted R square, and we can actually look at the F values as well. And just like we mentioned earlier, um, the box on the right, this is a stat output once again, tells you how many observations you're using. It tells you, and normally you want to have observations that are greater than 30 just for normality purposes. For running a regression, you want your data to be normal. But 30 is probably not a large enough number. Ideally, you should not have, you should not be running a regression with less than 100 observations. Uh, then you have the f value and the p value. The p value needs to be significant and the f value has to be greater than 4. This tells you that jointly your variables are your independent variables are better than a model where there was no independent variable. Then you look at the R square, and the R square is basically 36%, 36.35%. So you're explaining 36.35% of the variation in the wage. There is no hard and fast rule that talks about how much the R square should be. Anything more than 10% is something that can be defended. However, when R squares are very high, more than 80%, 90%, then your results become suspect because trying to explain something more than 90%, being able to do that would be very tough. And and the thing about R squares is that if you keep on adding more variables into as your independent variables, your R square will keep on going up. And this is a problem. Even if you keep on adding random variables into the as independent variables, your R square is going to go up. And to resolve this problem, there is another R square called the adjusted R square. Now the thing with the adjusted R square is that if you put a bad variable into your model, the R square will go up, but the adjusted R square will actually penalize you and start going down. So ideally, with your regressions, your R square and adjusted R square should be close to each other. Uh, Now let's talk about the left hand side of the regression output, and this over here is an ANOVA table, and I'm sure you guys have studied this in your statistics class about how there are things called the sum of square residuals and sum of square estimates, and this table over here is basically used to calculate the F statistics and the R squared. So if you look at this, if it's the mean squared estimate or the mean squared model, when it's divided by the mean squared residual, will give you the F statistics, and similarly, this is your SSE or SSM or sum of squared estimates, and this is your sum of squared residuals, which you see over here, and this is the total sum of squared variation in the residuals, and this is the total variation in your dependent variable, and out of this total variation, how much is being explained by your model is this much, and the remaining is being unexplained. Your model is unable to explain this portion. So if you want to figure out how good your model is, you divide how much your model is explaining out of the total variation in the wages or the dependent variable, and that gives you a value of 36.35%, 36% as your R square. Before I get to the lower half, what's very, very important to remember is that we are trying to explain how the world works, and we are trying to explain a phenomena that exists in the population. So we want to explain how wages of the whole world are impacted by education, but we don't have the data of the whole world. We only took data from 568 people from a specific place. But now the question is that if you took data from another sample, would you end up with the same results or not? And that is the real issue over here. And you'd probably be thinking if you gather data from some other sample, you'd probably end up having a different result. So this beta over here for education might be different. It might be 0.56 if you took a different sample. And then if you took another different sample, it might be 0.66. It might be different. So this kind of basically says that this beta value over here is dependent on the sample that you chose, which then kind of doesn't help us too much, because that therefore this means that you can't generalize your findings. You can't really say that what you found can be applied to everyone, and that is why we need to kind of go back into the statistics of things, and um, because we're unsure about how reliable the results are if we were to use a different sample. And just to reiterate, we want to explain how the population behaves using data of a sample. And in order to do that, what we're trying to do is if you were to take many samples and then calculate those beta 1, this beta 1, beta 2, and beta 3, and beta 4, um, on average, we want that the betas that we get should be equal to the betas of the population. And if we can do that, then we say that our estimate is an unbiased estimate. It, it tells us something right. And to do that, we calculate something called the standard error of the beta. And the standard error of the beta is basically how different is your beta from the true population beta. So there's some maths involved over here that is used to actually calculate this. And your regression results basically report this standard error. So this is telling you how is your sample mean beta different from the population beta? So, and it's like standard deviation, but not standard deviation, because standard deviation is within a sample, and this is basically between samples. It's like the sample mean being different from the true mean. How much is it? And using the standard error, if you divide by the coefficient, you end up with what's called a t-value. And then I'm sure you've heard about hypothesis testing during your degree somewhere. And this t-value can then be compared from a t-table. And one way to remember this is that if the t-value is greater than 1.96 or less than 1.96, you can say that your results are significant. Um, so it's basically hypothesis testing, and the easier way to go about this is to look at the p-values. So p-values basically are probability values, and they're basically telling you how confident are you with your results. That if you were to use a different sample, how confident are you that you would get the same result? And the probability value is basically 1 minus your confidence level. And with social sciences, if you're more than 90% confident about something, and then you say that there is a significant impact of this variable, I'm sure that if I used a different sample, I'd get the same result. So in this case, the p-value is greater than 0. Is 99%, is less than 1%, which is basically saying that so the p-value has to be less than 10%. If it's less than 10%, or if, let's suppose it was 0.10, this would imply that I am 90% confident that I'd get the same value if I used a different sample. If this value was say 0.029, so if you subtract this from 1, you end up with maybe 97% confidence that if I were to rerun the regression with a different sample, I'd get the same coefficient for experience, or similar, relatively similar coefficient for experience. So you want your p-values to be less than 10%. In our case, coincidentally, all values are less than 0.10, which is 10%. So we are confident that if we were to run this regression with a different sample, we'd get the same results. So the way to approach this is, so hypothesis testing is something maybe you might have covered in your statistical inference course. And the way this is done is that you make a null hypothesis, and the point of making a null hypothesis is that you want to reject it. So if you look at this equation where you have beta naught, beta 1, beta 2, beta 3, beta 4 along with some parameters, if beta 1 is 0, then 0 times education means that education does not have an impact on wages. But if beta 1 is not equal to 0, then education times this would impact wages. So you make a null hypothesis that beta 1 is 0. And then you want to statistically reject this to show that beta 1 is not 0, therefore there is an impact of education on wages. We want to reject the null hypothesis and show that beta 1 is some value, suggesting that increasing education would increase or decrease wages by the value of the beta. So that's basically hypothesis testing, and we've done it through t-values. So over here you have t-values. If you're comfortable looking at t-values, any value that is greater than 1.96, less than minus 1.96. Notice in our results all values are significant. We can then conclude that our estimation is correct. Let's go through how to read the results in a stepwise model method. First, you need to look at the model, And for the model, you look at this part of the result and you see how many observations you have. You look at the f value, whether your model is a good model, how well are your independent variables explaining the dependent variable. You look at the r squares and see if they're good enough. You compare the r square with the nested r square. You see whether they're similar to each other. If r squares are very low, you might want to include additional independent variables into the mix. If there is a difference between adjusted r squared and r squared, you might want to reconsider the variables, independent variables that you've added into the model. That's just looking at the model fit first. The second step is to look at the beta values. Now, these are the coefficient beta values. When you look at the beta values, you have to look at first the p values. Looking at the p-values or the t-values will tell you whether there is a significant impact of education on wages, experience on wages, tenure on wages, or gender on wages. If this value is greater than 0.1, more greater than 10%, then you cannot say anything about the effect of this independent variable on wages. You say that the impact of education on wages is insignificant if it was the case. In this case, it is significant and highly significant. So you look at the p-values, t-values, and check for significance. If p-value is greater than less than 0.1, say you said it's significant. There is a significant impact of the independent variable on the dependent variable, and similarly, you can look at t-values if you want. Once you've identified that there is an impact, then you need to talk about the size of the impact. A positive value tells you that increasing education will result in wages going up. If this was a minus value, increasing education would result in wages going down. So positive values tell us that increasing the parameter will result in the dependent variable increasing by the value of the beta coefficient. The negative value means that increasing parameter by 1 unit will decrease the dependent variable by the value of the coefficient. So you look at signs, and then you look at the magnitude as well, because with the magnitude also matters. Um, and with that, we stop over here, and then we go into practice. Next time, we talk about some panel data analysis.